For this calculation problem, topics 5 and 8 will be addressed. Part A will show turbulent internal fluid flow with friction loss, and Part B will show laminar internal fluid flow with friction loss. Part C of this problem will cover topic 8, external fluid flow. In Part A, the turbulent form of the Fanning friction factor equation was used after calculating the Reynolds number to determine the flow to be turbulent. The friction loss was then calculated, taking into account the minor loss from the sharp-edged exit. The cited properties from multiple handouts are listed, and the assumptions that the water was flowing at steady state, that the pipe was adiabatic, and that the water had constant density with no work were made. These properties were used for parts A through C. The friction loss was then calculated with the numbers given and the properties collected, and was reported in kilojoules per kilogram. In Part B, the velocity of water through the pipe was given, so Reynolds number could be calculated and the flow was found to be laminar. The Bernoulli equation was used to calculate the gauge pressure at the pipe entrance, which was in terms of the friction loss. The friction loss was calculated using the Fanning friction factor equation for laminar flow, also taking into account minor losses from the pipe exit. Part C, addressing external fluid flow, analyzed the flow of water over a rock in the river. The Reynolds number was calculated using the given properties and numbers, and this was found to be in the range of using a constant drag coefficient of 0.5, assuming the rock to be spherical. So the drag force equation was used, and the drag force could then be calculated and reported in units of newtons. For this calculation problem, topics 7 and 6 will be addressed. Part A will cover flow through porous media, and Part B will cover a pump analysis problem. In Part A, the extended form of the Bernoulli equation is first used to find what the friction loss term is equal to. Then, the ergon equation was used, as well as the equation for Reynolds number. It was assumed that the water was flowing at steady state and that the system was adiabatic with constant density. There was no change in kinetic or pressure energy and no work. At the given temperature, the properties for the density of water and viscosity of water were found. With the ergon equation, the superficial velocity was calculated, and from there, the Reynolds number was calculated and the flow was determined to be turbulent. For Part B, the equation for required net positive suction head was used, as well as the extended Bernoulli equation in its head form. For this part, the initial velocity was considered to be negligible, and the pressure at location 1 was assumed to be atmospheric pressure. The same properties from Part A were also used. The height that the water dropped in the ditch before cavitation was then calculated. This calculation problem will cover topic 9, compressible flow. The equations used in this problem were the stagnation equation and critical properties of sonic flow equation. The air was assumed to be an ideal gas, and its flow was assumed to be isentropic. Also, it was assumed to have a constant specific heat and be flowing steadily in one dimension. The value of K for air was looked up in handout 8A and found to be 1.4. In Part A, the stagnation temperature was found using the given values and the stagnation equation for temperature. This was then used in Part B to find the critical pressure of the air, which would be located at the throat of the converging-diverging nozzle. This calculation problem will cover topics 10 through 12, which will include microscopic mass and momentum balances, boundary conditions, and analytical and numerical solutions to Navier-Stokes problems. For this problem, the Navier-Stokes equations were used as the continuity equation in Cartesian coordinates, here,
and the x component of incompressible Navier-Stokes equation were used, shown here. Also, the equation for shear force was used, as well as finite differencing equations. Properties of water at 25 degrees Celsius were taken from handout 4, and many assumptions were made. This was to use the Navier-Stokes equations. These assumptions included that the fluid was Newtonian, incompressible, constant viscosity, no electric field, steady state, fully developed, and that there was no change in pressure. The flow was also assumed to be laminar. Utilizing these assumptions, the Navier-Stokes equations were simplified, as shown here, and the velocity profile in the x direction was found by integrating and implementing the boundary conditions. The shear force was then calculated in units of newtons. Finally, the numerical solution was found using finite differencing formulas. The analytical solution was graphed, and the numerical solution was also graphed, using a delta y of 0.05 meters.